G'day, I'm Veli from Greenwood Solutions, and sitting next to me is...
Hi, I'm Jayesh from Greenwood Solutions, and I'm a senior renewable energy engineer and CP NER in electrical engineering.
And today we're talking about protection and coordination studies. It's a really important part of the whole process when you're looking to put on, and in this case study scenario, a 500 kVA inverter system onto an existing manufacturing facility. It's actually an engineering company. And Jayesh and I are going to go through the process of what a protection and coordination study actually is, what's the definition of an LV system, and how it all works and why it's important. So I suppose the first question, Jayesh, to ask, what is the definition of an LV system?
So basically the LV system is typically any system which operates at 1000 volt AC or 1500 volt DC. The supply which we usually see for the residential, commercial or the industrial systems.
The 1500 volt DC, obviously that takes into consideration solar farms because that's what they're operating on, those kind of voltages. So we've got this LV system. What are the components that actually make up the system? What are we talking about here? Transformers and stuff? What?
Yeah, so particularly LV system would include step-down transformer, main switchboards, LV switchboards, if there is any between main switchboard and transformer, then circuit breakers, bus bars, cables or switchboards other than main switchboards downstream.
What we're talking about here from a protection coordination study perspective is electrical faults.
Yes.
And I know there's a few different kinds of faults. Can you sort of explain what they are?
So some of the types of the faults are short circuit, ground fault, arc fault, overload fault and open circuit fault.
Can you go through the different kind of short circuit faults that there actually are? Because I know there's a few different kinds.
Yeah, so short circuit fault might include line to line or line to neutral.
Yep.
Or three-phase fault, which is between three of the lines.
So that'd be the worst one. The worst
Yeah.
when all L1, L2, L3 are all shorting out.
Together. Yeah.
Yeah. Talk about the actual definition of a coordination study, because I had to wrap my head around it, because it's called a coordination study, but it's also protection. It's a protection study as well. Can you sort of explain that?
So the objective of the protection coordination is to use the protection device to minimize the damage and isolate the problem in an electrical system. The protection coordination study must be performed to properly coordinate all protective devices.
And this is because we're coming along to an existing electrical infrastructure and we're going, hey, we want to put on a 500 kVA solar system, so we have to protect that existing infrastructure electrically, and also our own electrical infrastructure, our own MCCBs or motorised circuit breakers, the whole cables, the whole bit, and at the same time we have to coordinate with the existing system as well.
Yes. So
it's multi-layered, isn't it?
Yes. So the protection coordination study will help us, like if there is any fault in the PV system, it will isolate the PV main switch, or if there is a fault in a PV inverter, particular inverter, it will isolate that particular inverter breaker rather than tripping the upstream breaker in the main switchboard.
Is it a case that the thing that trips first should always really be the solar that we've added to the existing system? Is that a correct assessment? Or
if we are doing the protection coordination study particularly for the solar, we would want the solar breaker to trip first rather than the existing infrastructure.
Because the last thing a business owner wants is, let's say they've got a production line for it suddenly to fail. So the solar is the sacrificial lamb in a way, isn't it, when it comes to these protection studies? Now, I got to ask, this is something that the average Sparky or even the average engineer can't really do. You need a special program to do this, don't you?
Yeah. So there are a few programs which we use to perform the protection studies. Like we first use AutoCAD to draw a single line diagram with all the settings, which are some of the settings which are existing on site.
Yep.
And request the electrician to verify if all those breakers are set correctly, what's mentioned in the single line diagram, and then the distributor will provide the information of the transformer and its impedance and everything. Based on that, we put all the information we have in a PowerCAD software, or there are other softwares as well. So we run through a study in PowerCAD and try to identify if the system will work fine once the PV system has been installed.
Yep.
Or if there is any fault, what are the faults mentioned in that system, and trying to identify those faults and how those faults can be rectified.
Now, we know that electrically we need to ensure that we're not damaging the existing electrical infrastructure, that the insulation on the cable is not compromised, that the circuit breakers are doing what they're supposed to do. So there's this intrinsic relationship between the existing electrical system, as we pointed out, and what we're putting on. And it seems to all come down to the settings on the circuit breakers, doesn't it?
Yes, it does. And we can consider like the settings of the circuit breaker would be in LSIG, so long term.
Yep.
When it operates nominal, and if the nominal current is affected, they might sustain until particular period of time, that's called long time.
Yep.
Then S means short time.
Yep.
So the circuit breaker will allow the current to pass through for a particular time,
Yep.
short period of time, the higher current will pass through that, and then instantaneous. If the circuit breaker thinks that the current is going over its limit,
Yep.
it will trip instantaneously. And G is ground fault. If the ground fault occurs, the circuit breaker will manage.
So what we're talking about when it comes to the instantaneous trip, that role is addressed by the magnetic functionality of the circuit breaker. And you can sort of tweak it a little bit in regards to its response times, can't you?
Yes, so you can tweak it from 2 times till 15 times based on the nominal current. So for example, if your circuit breaker nominal current, because we are talking about 500 kVA system,
Yep.
the breaker would be 1000 amp, for example.
Yep. Yep.
So if we have the breaker of 1000 amp, the instantaneous strip might be, we can set the instantaneous strip to multiple of 2, which would be 2000 amps, or it can be multiple of 15, which is 15,000 amps.
So let's consider a system, 5 110 kVA inverters. So you're talking about 200 amps each and a cumulative of 1000 amp. Does that main solar breaker, does it have to be set a little bit differently from, let's say, the main breaker and the main switchboard from a time-wise?
It all depends what the upstream breaker is.
Right.
So if it is 2000 amps and then the downstream breaker for the solar we have 1000 amps.
Yes.
There might be some of the settings which you might need to play around to coordinate the 2000 amp breaker with a 1000 amp breaker.
Yeah.
So the 1000 amp breaker operates first if there is any fault.
Right.
Downstream.
Yeah.
Of those 1000 amp breaker
Right.
rather than 2000 amp breaker tripping.
Right.
Which might affect the overall load of that production factory also.
Yeah, okay, so, and that's the important thing, as we stressed before, that we're putting something onto an existing system that we do not want to affect that existing system in a negative way. So the solar becomes the sacrificial. It's the first line of defense if there's a fault current in that area. With the protection study, does it suggest within the study to the installer what settings he needs to set those breakers for?
Yes. Basically, when you perform the protection coordination study, you put through all of the settings which are actually present on site. Right. For the existing system, which can be long-term, short-term, instantaneous, and ground fault settings, which are already present at the site. And then when you are performing this study, you adjust the PV system settings or PV system breakers settings. For example, here 1000 amp breaker as well as 5 of the 200 amp breakers settings to coordinate with the main switchboard or the existing system. So basically you get the settings of the PV system main switch as well as the inverter breakers which are coordinating with the upstream or the main switchboard.
And what if there's and there'd be distribution boards as well? So the breaker within those distribution boards, or the breakers, they would be included in the study as well?
Yes. So basically, when you are performing the protection coordination study, let's go from the downstream side to the upstream side.
Yes.
So basically, we perform the study from the inverter to the inverter breaker. Then PVDB main switch.
Yes.
Because there might be multiple inverters.
Yep.
Then it goes up to the, for example, if the PV is connected to the distribution board.
Yes.
So the PV main switch would be in the distribution board, and then it would be going through the distribution main switch.
Yes.
And then in the MSB, for example, that DB is connected in the MSB. So it will be going through the DB main switch in the MSB, then main switchboard main switch.
Yes.
And if there is LV fuse or circuit breaker, we will consider those settings
as well.
And then the transformer settings and its impedance. So we might get the HV fuse ratings, transformer ratings and its impedance.
Yep.
Then if we have the LV breaker or LV fuse present at that particular site, we will get that information of their ratings and everything. Then we come to the main switchboard, main switch. So what the main switch is set at and what are the settings of that particular ACB or MCCB. Then downstream of that might be a distribution board main switch which is connected to the MSB main switch.
Yes.
So we might get the settings, what are the settings of the distribution main switch. Then jumping down to the distribution board, so settings of both the breakers in the distribution board, which is distribution main switch as well as the solar main switch settings, which we can provide as well based on the coordination. And then below that there will be a PVDB main switch and then the inverter breakers, multiple inverter breakers. So settings for those can be like, because it's addition to the existing system,
yes,
we can provide the settings for those particular breakers and we can play around with the settings of PVDB breaker settings because that's the new installation and which can be easily winded down to the settings which is required.
It's quite a complicated area, this, and you need to get it right. And there is, under AS 3000, there's a certain size systems that you need. They require a protection study, and I believe it's over 800 amps.
Over 800 amps, it's must have, but it is also depending on the distributor, the energy distributor. When you put through the application, they might request you for the protection studies for maybe over 200 kVA, and some of the distributor, while submitting the application, you might need to submit the protection coordination studies as well.
Yeah, because they're obviously worried about the line side, you know, their infrastructure. They really don't care about what goes on the load side of things.